Electronic Project 6, Designing Logics with Flip-flops and Latches. In this video, we try to understand the difference between latch and flip-flop. Okay, so what is the difference between latch and flip-flop? So this is a typical SR latch or RS latch, whichever you call, and actually this is a section of the latch. So what happened is the latch, you have a set. If it's active low, when it's low, it's forced to the Q to be high, and this is high, and there's no clear, then this goes low. So you set output high, that's a set, and clear is the opposite. You set Q bar high and Q will be low. Okay, and what happened is this is S and this is R input, and S and R normally high here, they never go low together. And if S, this is bar actually, S is high, this goes low, so same effect as set, and R goes low, it's an active low, so it's same effect as reset. So that's why set and reset latch. When both are high, what's happened is whatever the previous logic state, say Q is high, then this is going to be all high, then Q bar is low. So logic state Q is high, Q bar is low will stay same as long as set and reset both are inactive. So you can change the output by set and reset, but if you activate both, then the state is not going to be logical because both Q and Q bar become high. So the logic state of SR latch is like this. If both are low, then Q will be previous state. Okay, and this is opposite. S set high, then this is going to be 1, 0, and reset goes high, then this is going to be opposite, and both high, this is unknown. Q and Q bar, actually it's not unknown, both are high, and this is a violation of QQ bar, so this state is not used. So SR latch, either S or R become active or both are inactive, means retain memory. Memory means previous logic state. So as long as SR are low, it's hold the previous logic state forever. So whatever retain the memory, it's a memory, right? And before we get into that, we have to talk about the latch. Okay, since we make sure always either one side is high or both are low, we guarantee that by adding a gate here. Means enable, when enable is low, then both are inactive. Okay, which memory, holding memory state. And enable is high, then it's enabled, that means the data can go through. This is going to be D, and this is going to be D bar. So we're talking about this area. Okay, so D-latch use only this state. Okay, so it's guaranteed to be logically correct. So that's a D-latch. So D is for data. Data come in. And enable means enable store the data into Q and Q bar. Okay, so Q and the Q bar remember, and the enable goes away. So what's happened is it's remember the data. So that's why it's called latch. Latch means remember the data. Okay, and this is actually the 1 bit of static memory device. And you have many bit, say 64 bit of them, and the output is ganged together, and you select by address decoder. Address decoder select one of them. Then you make a logical AND, or gate, and summarize the output. If you have this address decoder, that's become the memory chip. Okay, so basically memory is the latch, the latch, many of them. Okay, the latches, many of them, and select which latch to use by address decoder. That's the memory chip, and you need a write control. Okay, and how do you control write? So you have to know the latch write control works this way, right? This is enable. When enables high, then data come in, and data may be changing around and stable before enable goes low. So this is the logic state, either Q is 1 or 0, and hold that memory here. Then when enable goes high, the data start changing around. Okay, so if enable is a clock, the latch hold the data only for half cycle. Okay, this period it's a hold the data. No matter how you change the data, it doesn't change. Output is going to be stable. Then it start changing again, depend on D. Then it's latch up. This is latch up point. Okay, so timing wise, there is a latch up point. Once it's latch up, half cycle, it's hold that data, then go away. So the write control for memory, when you write, you give write pulse, and whenever data in, you write that data into the memory. I'm gonna change it around, and better be stable before latch up point. Then data is written into the memory. So memory need the write enable. This is called write enable pulse. And the write to enable pulse, the trailing edge is a latch up point. The data in has to be stable before that trailing. Okay, then it's latch up the data. Then it's stay disable. This is bar disable. Then the memory content is held forever until next write cycle. Okay. So the logic design, this is a problem here. The latch hold only half cycle the data. So what we do is we modify, we cascade the latch in this fashion, and enable, we invert the priority and give the enable this. Okay, so it's going to be, what's going to happen is this is going to be called flip-flop. So the first half cycle, you take in data and latch up here, right? And since it's inverted, the next half cycle start this moment, you transfer this into this. So data is transferred to be here. Then next half cycle, data start changing here. But since output is controlled by the second latch, output will be stable. So I show you in the timing diagram. Say you have a clock. Right? And here you're going to latch up. So D may change around and become stable before latch up point. So D becomes stable, but as soon as the half cycle over, it's gonna start changing again, right? And wait until next. Okay, but D0, what's happened is D0's latch up point is here because it's inverted. So what's happened is this D is going to be stable during this period, right? And also this latch up point D, during this D, the second latch is transparent. It's not holding data. So whatever the D is going to be showing up at the Q. In the second half, you latch up in a second. So again, the D stay same. Okay, so the D0 is going to be like that. And actually, it's going to be Q0, Q output. It's going to stay. Then next clock, it's going to be different data. So it's a full cycle of the clock. The data is stable. Whatever it's latched up in the beginning, stay entire cycle. So second latch is used to stabilize data for the second half cycle. Okay, and here's another latch up point. You latch up a different data. So overall, it's look like this. You have a clock, then output data is going to be stable here, and latch point if change low and change high. So every latch point the data change depend on D. Okay, so what the flip flop is? Flop means flip is the first latch action, and transfer that to second stage, that's a flop. Why do you do that? Because to make the output stable for entire cycle. So whatever the data coming, it's going to be captured and hold it stable for entire circle, clock cycle. Okay, so the data is captured at the edge of the clock. It's called edge triggered. And edge triggered, you can have, if inverted clock, the rising edge triggers or falling edge triggers. You can have two kinds. The important thing is hold the data for entire clock cycle. So how do they make a you have flip flop, you make a, this is a little modified concept, is because you take care of clear and clock D and set and clear use one SR latch, and the clock D use the first stage and this second stage SR latch. If you follow this diagram, you will see how the data is captured here at the edge and transferred to the another edge of the clock. So clock edge triggers, and this edge is flip and flop, and meanwhile output is going to be whatever captured here stay whole cycle. Okay, so this IC chip 74LS74 has such a flip flop, two of them in a single chip. Okay, so what can you do with only two? This is the example. Say we have a control on one of input, flip flop, and the clock is common. So both of them update the memory content at the clock edge, same clock edge. Okay, then this output and this output go through NAND gate. This is 74LS00, and output is going to be fed back to the second flip flop D. So what happened is this guy has a control. If this is high, this will be high when clock arrive, and this is high, so it's up to this guy. If this is low, then it's high, and this changed to high, and both are high, so it's changed to low and changed to high, so and so. But if you turn this to low, then this is low, the NAND gate is always high, so it's high become high, and doesn't matter because this is low, it stay high. Okay, so we put the LED and observe. So the clock it's you use a digital clock, it's too fast and you cannot see this transition of the logic. So we use the one made by 555 timer, generate very slow single pulse. Okay, we control the clock. This 555 timer circuit, we details in the previous video you should watch. Then we can generate manually the clock pulse one by one. Then we see this logic transition. So this is going to be control switch, control state machine. Okay, this is actually become microcontroller. Okay, now when this control come from the memory, it's called program, the program control hardware. So that's a microcontroller. So when you get more complicated, more flip-flops, more logic, it become microcontroller. So this is ultimate goal of understanding digital logic. Register is a group of flip-flop. For example, like 16 of them. 16 flip-flops. And you have a logic. It could be ALU. Then you give a clock. Each clock, it's calculate ALU. Then it's go back. Result is fed back. Well, in the real microprocessor, what's happened is you have many register A and register B, and you have same clock going, and both go to the logic ALU, right? Then output is going to go back to A, and the B fetch another data from the memory. So you can do, say, addition of data from memory. Say you fetch one by one and add it, accumulate into the register A. So this is CPU, right? So you now it's very close to understanding the nitty-gritty part of the CPU at the logic level. Okay, so that's the ultimate goal for this project. Now, of course, we do some analog circuit too. So our objective is much broader than just understanding CPU. Okay. Okay. So flip-flop. This section. Oops, it's floating switch. This section is a previous video to generate the single pulse using 555, and this single pulse is used as a clock. This clock goes in here. This is 74LS74 2 flip-flop, and this is 74LS00 NAND gate. And the reason why I got messy is every reset enable line I needed to tie to the high, because detail input, basically if you don't connect anything, it's high, but it's a high impedance input. That means it's like antenna, and little noise suddenly get the pulse and change the logic state. So it's good practice to connect all the unused reset signal. It's usually made active low, so it's connect to the high state, the 5 volt, so it's stable. Because when you try to measure some voltage and it's a slight movement, it's going to pick up and change the state. And this floating this switch is the manual control whether give high or low to the one of flip-flop input. So we give the first power shot. Okay, so this light up. Second, turn off. Next clock, it's turned on. And this is the right now off state, means the one of flip-flop input is high, so it's toggle. But once you change it, okay, now I short circuit the ground to the input, that means low. Then this light stay on. Okay, there was a loose wire, that's why. Now I bring it to high, then this guy start alternate. Okay, so very slow clock. Each time clock coming, it's alternate. But once you turn on this one, that means low, it doesn't change, it stay on. So exactly as expected, this is the output of the NAND gate. Okay. Okay, so we look at more details about this operation. Suppose this is a control D1, right? And when D1 is high, what's happening is when clock arrive, this is going to be high, right? So when this is high, then NAND gate depend on this guy, and we don't know, this guy could be high. If high, both high, then it's gonna be low, and next clock arrive, it's going to turn into low. So when it's low, then this is going to be high, so it's repeat. So when D1 is high, the output will be low, high, low, high. So it's alternate by each clock. But if D1 is low, then what happens is this guy get low. So this NAND gate permanently give you high. So it keep latching high here. The flip-flop input high, every clock arrival is gonna be high. But this high doesn't affect because this is low. Okay, so the output stay high. So this is a control, and this is the output result. Okay, so we can have a much more complex logic here in this box and create all kind of logic machine. Okay, so I hope you enjoyed this video, and if you like, subscribe and keep going with the next video.